I would like to thank the organizers for giving me this unique opportunity to speak here. I know Kalyanda and Srinivas for last 20 years, more than that, who taught me in several occasions in my PhD times. So it's a great occasion to speak in their 60th birthdays. So today I'm going to speak on non-vanishing of kernel functions and Poincar series for Jacobi forms. So this is a joint work with my PhD students, who is now a postdoc at TIFR, Sivan Pandey. So let me. In a talk, Kanika talk about this L function associated to the Hecke eigenforms. So let's start with the notations. Let Mk be the space of modular forms for weight k for the full modular group, and Sk be the space of cost form of weight k for the full modular groups. So given a non-zero Hecke eigenforms Fz with Fourier coefficient an, we associate the Hecke L functions with this summation an by n power s, which makes sense for real s bigger than k plus 1 by 2. And we computed the L functions with this 2 pi, with this 2 pi minus s and gamma s. And we know that this has your holomorphic continuations to whole complex plane and satisfy these nice functional equations. These particular functional equations, and it is well known that the zeros of this L star, the computed L functions, occur only inside the critical strip k minus 1 by 2 less than real s and between k plus 1 by 2. And according to the generalized Riemann hypothesis, we expect all the zeros should lie on the critical line real s is equal to k by 2. Okay, so just to speak interesting result of Winfried Koenen in 1997, he proved a non-vanishing result of L function on average. He proved that if we have a basis f1, f2, f, this is like dimension up to dimension sk, be a basis of normalized Hecke eigenform for the cost forms of weight k, let T naught is a real number and epsilon positive, then there exists a constant depending on T naught at epsilon positive, such that for any k bigger than the constant, the functions summation I from 1 to dimension sk 1 by this fi with fi inner product with L star fi s does not vanish at any point s is equal to sigma plus it with this t equal to t naught from this particular line segment with sigma k minus 1 by 2 with k minus with between k by 2 minus epsilon and k plus 2 epsilon less than sigma less than k plus 1 by 2. So this is the non-vanishing of the L functions on the average. So there is an interesting corollary. One can find that for T naught and epsilon positive, for k bigger than this particular constant, and for any s sigma plus sigma equal s equal to sigma plus it with t equal to t naught, and between these sigma, there exists a Hecke eigenform f in the cost forms, so that this L star value is not equal to 0. Actually, this I think in 2021, Professor Kumar Murthy gave a talk on the Ramki's 60th birthday through online Zoom. So that time he talks about these functions. So I got to know about this. Let me just tell about that. So the Koenen used certain kernel functions for the proof, and the proof looks very elegant. So basically for z in the upper plane and s equal to sigma plus it in the complex plane, so between sigma 1 to k minus 1, Koenen defined these kernel functions Rksz, this summation with some gamma functions s, gamma ks, and this particular, let me write these functions is basically, if you take this to the power tau to the power minus s stroke a b c d with k and sum over this particular a b c d, that's the functions we are talking about in the kernel functions. And we know that Koenen proved that this Rks is a cost form of weight k, and for any f in the cost forms, we have this particular inner product, that f inner product with Rks bar gives up to some constant the L star values of this corresponding f. So we know this that the Poincar series gives the nth Fourier coefficient, nth Poincar series inner product gives the nth Fourier coefficients, and we can get the L star value through the Mellin transform of the function f, but this kernel function inner product gives this L star the completed L functions. And he also further proves that these RKS, the kernel functions, one can write in terms of the infinite sum of Poincar series. And what the Poincar series is the usual our SL2Z Poincar series for the SK. What the theorems, the main theorem of the Conan prove is that the RKS he explicitly compute the Fourier coefficients for this particular RKS. Let the Fourier coefficient be RKS small n, where the small n looks like some gamma functions and some of the is similar to looks like the Poincar series coefficients with some of these the Bessel functions, Kummer's hypergeometric functions that appears in the coefficients looks complicated, but one can deal with these sums, and he basically proves that to prove the main theorem that non-vanishing, he write the RKS, the kernel function in terms of this linear combination of the Hecke eigenforms to get this particular format. And basically he proves the main theorem is that the Fourier coefficients RKS n, he proved that RKS 1 is not 0 for S in the left plane of the region where we talk about for the large K. So basically he duly the Fourier coefficients in some analytic estimate so that this function is not 0 for the large K. So one can explicitly also one can find how large the K can be, and then you have suppose looks like this. So you compare the nth Fourier coefficients and you can see that the sum of this sum is not basically non-vanishing for the large K on the left region, and using the functional equations one can get the non-vanishing for the whole region. And this functions, the Conan construction is kind of in some very useful, and there are a lot of works. I think Conan and Sengupta generalize this construction of kernel functions to prove this analytic condition of the Koser mass series for the Ziegel modular forms in 2002, and there are further works like for the Ziegel modular forms, Someo and Conan generalized for 2018, and recently for to generalize the Hilbert modular forms. So I was talking about Manikam, Kumarmurthy and Sandeep. They proved this non-vanishing of the kernel function RKS at the point I for certain real parameter S equal to sigma inside the critical strip, and they do analytic estimates and deduce the non-vanishing of the weighted L values of this particular Hecke eigenforms. So we try to generalize this work to the case of Jacobi forms. That's the aim of this talk today. So let me just give a small brief introduction as far as Jacobi form is. So Jacobi forms, we have this SL2Z semi-direct with Z2, this element size of the type a matrix and a X elements, a lattice with the groove law defined like that. And the groove, Jacobi groove act on this H cross C, the space is H cross C here by this particular actions. So ABCD, this is SL2G matrix, and lambda mu that's coming from the lattice, and this act on this lambda tau z in this particular forms. And one can define this for a fixed integer k and m. We consider this automorphic vector j k m h tau z, this particular c tau plus d that appears minus k, and this come from the lattice section coming from here. So now one can define Jacobi forms. So Jacobi forms on kind of the functions, the gamma j, the Jacobi groove act on the function on the S cross C by this particular stroke operator, phi stroke km h tau z in terms of this particular automorphic vector, and this corresponds the action from here. And we define Jacobi form now that given a positive integer, given integer k and m. So Jacobi form with k index m over the Jacobi gamma g is a holomorphic functions which satisfy this particular invariant property for all h in the Jacobi groove, and has a Fourier expansion similar to the case of modular forms phi tau z in terms of C n r q and zeta, q equal to exponential 2 pi I tau and zeta is exponential 2 pi I z, and the sums over n are in integers with this particular condition 4 m n bigger than equal to r square. So furthermore, we say the Jacobi cos form is Jacobi form phi is a cos forms if it has this particular Fourier expansion where this n r belongs to z, but the 4 m n strictly bigger than r square. So to the case of like the case of modular forms, this Jacobi cos forms this form a vector space, and also have a and Peterson inner product, which makes this to be kind of space to be Hilbert space, finite dimensional Hilbert space. All right. So we have this kind of Eisenstein series example, and we have these Jacobi theta functions, which are half integral weight Jacobi forms. Also, if you look if we take Ziegler modular form weight k degree 2, then the Fourier Jacobi expansion, we have this capital Z. Capital Z is something like tau Z, Z tau prime, and the tau and tau prime are upper half plane variable and Z in the complex variable. Then f of Z is the Fourier Jacobi expansion like this, and you can see that the phi m tau Z, this is a Jacobi form weight k index m. So Jacobi forms of weight k index m appear as mth Fourier Jacobi coefficient of his Ziegler modular form of degree 2, and these are to be natural generalization of the usual modular forms. Okay, there is a nice arithmetic coming from the group actions, namely the Fourier coefficient of a Jacobi form satisfy this particular invariance, namely C n r equal to C n prime r prime, whenever r prime and r is related by modulo 2m, and this particular 4 n prime n minus r prime square equal to 4 n m minus r square. So we call this to be discriminant coming from the index. So if the C n r equal to C n prime r prime are equal whenever they are related like this. So this conditions, we can build up this L function associated to that. That's the important thing here. So we set off CRD to be CNR, ED equal to looks like 4NM minus R square, else you put the CRD to be 0. And we define, we're trying to define this Dirichlet series associated to Jacobi forms. We are moving towards that. So we define this theta m mu tau z equal to this particular Jacobi theta q r square by 4m zeta r, where this r belongs to z, and this r is congruent to mu modulo 2m. And similarly, we can define this, we have this Jacobi form weight k index m. We can write this Jacobi forms in terms of the finite 2m sums of h mu tau theta m mu tau, where this h mu are these particular half integral vector valued half integral modular forms like this. So to a Jacobi forms of weight k index m, we have this called the theta decompositions of the Jacobi forms, which relates with the half integral point of the theta series. And we associate this, the Born 1994 associate this 2m tuple Dirichlet series like this. So L mu given a mu from 1 to 2m, we have this particular phi s, where the c mu d and d to the 4m to the minus s. So we have similar, we completed these functions lambda mu of phi s, and these are kind of studied by the Born. This is uniformly convergent on the complex of real s plus bigger than 2, k real s bigger than k by 2 plus 1. Also, we Born defined this, studied also the use Martin, they studied these analytic continuations of this kind of Dirichlet series, the 2m tuple Dirichlet series. So let's, for a Jacobi forms of weight k cos weight k index m, we define this phi bar tau z defined by this particular transformations phi of minus tau bar comma minus z bar and the whole bar, and we see that this is also a Jacobi first form of weight k index m, and the corresponding theta decompositions, instead of in the place of h mu, the c mu into sub c mu d bar appears as the corresponding form there. And now this was put by Martin in 2014 that if you take this weight bigger than 6 and m be a positive integer, and you take a Jacobi forms of Jacobi cost form of weight k and index m, then every completed Dirichlet series lambda beta phi bar s with beta 1 to 2m admits analytic continuations to the whole complex plane, and they satisfy the set of 2m functional equations. For every beta, we have a kind of functional equation on this side. Okay, so we will try to generalize the work component to the Jacobi form setup. So also we have a kind of kernel functions that defined by U Martin. So in the case of Jacobi forms, we have this one more parameter coming to the picture. So S is complex plane, and we have the real S between 1 to k minus 3, and you take this T naught, another parameter that coming to the picture in the Jacobi forms case. So basically we take this phi T0 T naught comma S, where the phi T naught is appears like this. Why we know in the Jacobi forms case, in the modular form case 1 by this term appears, and the Jacobi forms get this extra term coming from the lattice. So this stroke summation in the corresponding from H actions, where this gamma g, this is the coset derivative coming from the stabilizer of this action coming from here. And one can take a coset derivative of the elements given by this particular set. So then Martin proved that if you take this particular parameter, wave complex plane with this real S between k to 3, this series, this defined as Jacobi cost forms. In the paper you prove this is defined as Jacobi cost forms. And moreover, we have this inner product with phi with the we call the kernel functions that gives up to some gamma function and pi factor, where this particular exponential sums in terms of these two m many sums in the case of Jacobi forms, we have the exponential sum and the lambda p, the Dirichlet series come into picture in this case of here. In the case of modular form, we have one Dirichlet series, but here a tuple of Dirichlet series that come into picture. And he proved that this inner product gives particular expression in terms of Dirichlet series, and for all phi and for all s with this particular range. All right. So we following this result of Cohen, we compute the Fourier coefficients of the kernel functions for these Jacobi kernel functions, and we see the non-vanishing of the general nth coefficient of this particular kernel functions. So this is the theorem we prove is joined by Sivans. We prove that for this particular range of k bigger than 6 and the real S between 1 to k minus 3, we have this particular Fourier expansion of the Jacobi cost forms WNR, when the WNR is a similar kind of functions that Cohen deal in the kernel functions, but we have to have some more variable coming from here, as the Jacobi are in terms of lattice and the groups are different. And this is the Kummer degenerate Kummer functions that appears in the case of that also. So basically, these are wanted to do with some of the integrations and in the sum of the lines that have to find the Fourier coefficient in the case of Jacobi cost form, like in the case of modular forms. And second theorem that we prove is that the WNR is the forms is the nth coefficient that we wrote in the last slide. Then given positive integer m and r with this condition coming to the picture coming from the actions, that there exists a k naught, so that the WNR not 0 for k bigger than k naught. So one can find the k naught explicitly with some bounds. So we also prove that the similar theorem that shown by this Cohen, that if we take this particular some t prime bigger in the real epsilon positive, there exists a constant k naught depending on the t naught and epsilon, so that k bigger than k naught and s in sigma plus I t prime with this particular range. We have there exists a Hecke eigenform Jacobi cost forms, so that the vector valued forms this is not equal to 0. This is the generalization of the Cohen theorem for the case of Jacobi forms. So let me just give a brief case. Is more or less is the Cohen's idea we will follow in the case of Jacobi forms also. So to prove the theorem in the region that we talk about, we have this line of symmetry k by 2 minus 1 by 4. We have this for S equal to this particular one with delta between 0 to half. Then we write and we have a basis of Hecke eigenforms. So we write these kernel functions in terms of these expressions in phi I with this particular inner product ratio, and now we compare the nth Fourier coefficient both sides, and using the non-vanishing coefficients that in the one of the theorem we proved earlier for given S, there exists a k naught, so that for k bigger than k naught WN are not equal to 0. So now we write there exists a Hecke eigenform, this coefficient not equal to 0. So we can say that there is a phi naught, so that this coefficient is not equal to 0. Now using the Hecke eigenform and the functional equations, we complete that the lambda beta is not equal to 0 for certain phi I naught. So this the basic structure is same to the prove the Cohen, but wanted to deal with the different kind of Fourier coefficient that appears in our case. So as you see, in the case of modular forms, in the usual kernel functions, we can write this in terms of the infinite sums of the Poincar series. So one can expect, because the kernel function is non-vanishing, one can expect non-vanishing of the Poincar series. So there is a non-vanishing of Poincar series, one of the important questions that we deal with. So there are conjecture of the Poincar series. So in the case of elliptic modular forms, where the result of Rankine, that there for a given there exists k naught, k bigger than k naught, and particular m, finitely many m's that depend on the something like less than k to the power 2 minus epsilon, finitely many m's, so that p k m not equal to 0 identically. So the same one can expect similar results. So as a consequence of our result, we try to see what kind of consequence we are given with that. So just to say, in the case of Jacobi, also we have this expression of the kernel Jacobi Poincar series. One can write the kernel function in terms of the infinite sums of the Poincar series. So just to say that in his thesis somewhere in 2010, he proved this is the definition of the Poincar series for the Jacobi forms, and one can write down this Fourier expansion, and that also deal with the generalized closed domain sums. And it's known that this Poincar series generate this space of closed forms. So in his thesis, somewhere proved that for pi d, the discriminant 4n minus r square, let's suppose pi d bigger than or equal to 2m, then the p, k, m, and r not 0, provided this d discriminant satisfy this particular condition. Okay, the discriminant equal to 4m minus r square, so there is n coming from here. So there is d, from the d relations here, there is n coming from here, and the Jacobi forms are c n r equal to c your n prime r prime. So and whenever these discriminants are equal, so this kind of there are finitely many n's for which we prove that the p, k, m, and r not equal to 0. That's the result proved by Somya in the case of Jacobi forms. And actually this comes from the Rankine, this particular expression comes from the Rankine's proof also. Okay, so let's try to see, because our kernel functions are infinite, one can write this. This also proved by Martin in 2014 paper, that for this particular range, this Jacobi kernel functions which can be written in terms of this infinite Poincar series. Okay. So since we proved that Wn are not equal to 0 for these kernel functions, and we proved that with even the given positive n r m, choose deltas between this half minus 2 delta between this. For k bigger than k naught, the Poincar series p, k, m, and r not equal to 0, where one can take k naught to a maximum of this kind of quantity. Actually, this comes from the proof when we prove that Wn are the Fourier coefficient not 0. So k bigger than k naught, one can write this k naught in terms of these functions. So we can write some of the functions that's coming from the WNR functions. We worked this 2 years before, and the last year we tried to generalize this work of Martin and this kernel function constructions to the Jacobi forms for the matrix index. So here the group is SL2G semi-directed with the ZG1 cross ZG1. In place of G equal to 1, we get this particular Jacobi forms of G equal to 1 is called the genus of the Jacobi forms. And the Jacobi group act on this space now H cross CG1. So it's similar to like that. So similarly, one can generalize these actions for a positive into n, and here the index is positive definite semi-derivative hypothetical matrix of order G cross G. So one can define this particular automorphic vector for the case of Jacobi forms of matrix index coming from the M here. And one can define Jacobi form for matrix index, the function from H cross CG1 to C, satisfying this particular Stokes operator as you see earlier for these general things. And also it has Fourier coefficients C n capital R, E n E r Z, or this is something like R is a vector now. So it becomes R1, Z1, R2, Z2 plus R and Zn. And where these particular conditions that generalize the condition of this 4n minus R square in the case of usual Jacobi forms. So we have so in the case of Jacobi forms, we also construct the kernel functions from the matrix index. Also, we prove that this for the large weight, the coefficient not equal to 0, similar to the theorem for the theorem 1, 2, 3. And also, we see this non-vanishing of Poincar series in the similar equation, okay, this is studied by Boker Conan in their paper sometime. They have completely write down the Poincar series for expansions, and we prove this similar Poincar series for the matrix index also not equal to 0, where this particular k naught come into picture. For large k, k bigger than k naught, and these are coming from the result from the general index. So one can show that the Poincar series does not vanish for a large weight like that. And these are consequence of the kernel functions that appears in our work of the matrix index functions. And these are some of the reference we published appear here, and this is just we submitted here. And this paper of Martin that talk about the kernel functions and the bond in that case. And this is the paper of Conan. He constructed the kernel function and proved this Nonvanishing L function on average on the critical strip. And I'd like to say happy birthday to Kalyan and Srinivas. Thank you very much for the attention.
Any questions? Oops, I think this let go. Any questions? Yes.
Sorry. Regarding the first construction of Conan, is there a way to modify it to say something about LS, sim square, or ranking Selbach?
Yeah, okay. The construction of kernel functions.
Yes.
So
yes.
in general, if we have a kind of a functions from like the SK to C, if you, in general, one can, since I have to construct this, so we have a space from SK to C. So this functions F goes to the L star F of S. So fixed S, something like this. So for a fixed S, something like maybe some TS, something like that. So this function is linear. So one can talk about this by this Hilbert space theorem, by redistributive theorem, there you kernel that. So how the kernel looks like, that construction one have to deal with that. So whenever there is linear forms from a linear function from a two Hilbert space, then one can associate the kernels.
Okay. I have one more question.
Yeah.
Is there a way to make the bound of Conan effective? Like he's saying there exists some weight after which you have non-vanishing, right? Can you tell me what that weight is depending?
I don't know, Professor Kumar Murthy might tell better because they have. You want to make the bound k not to be, or you want to find a f explicitly? That's your question?
No, I want, so I take a point S in that, inside the critical strip.
Yeah.
And then what is the k in terms of f? What is the worst that k can be?
I think in the paper of Professor Kumar Murthy, they proved that for these kernel functions, they evaluated at certain point like I for the real parameter sigma between this in the strip. And they proved this is bigger than some number.
Okay. Okay.
For the I think that is for general k. So.
Okay. Okay. Thank you.
I think some cases have been studied.
I don't know. I asked Martin, but he also said, because this Amrita is here, she was working in that one. So he said that he's also waiting for the definition that it seems like not yet defined.
Yeah, there are vector series we associate with the type Rankin-Selbach type, but the one we discussed, they don't have a good kind of L function, this Euler product kind of object.
But anyway, if you find somewhere, please let me know. Yes, thank you.